Okay, so we have discussed in detail about nozzle operation and diffuser operation. So we did a numerical on nozzle operation. So now we will focus on diffuser operation, and further on we will do few more numericals covering combined concepts. Several concepts that come together when discussing varying area flows. So let us see one by one. Okay. So first here this is a case of a diffuser, that is an intake diffuser. A supersonic inlet as shown in figure is to be designed to handle air. Properties of air are given. Gamma R is 287 at Mach 1.75. So this is entry Mach number is 1.75 with static pressure and temperature of 50 kilopascal and 250 Kelvin. So P1 is 50 kilopascal and T1 is 250 Kelvin. Determine the diffuser inlet area. So see, notice the kind of inlet that is described over here. There is a wedge that is protruding into the flow. So this is more in the lines of a mixed compression kind of an intake, where there is an external compression taking place by means of an oblique shock, and further there is an internal compression also happening inside the duct, and there is a possibility of a normal shock also occurring here. So there is a normal shock here. So two shocks and then variable area duct. The diffuser is further to the device is to handle 10 kilogram per second of air. The diffuser is to further decelerate flow after the normal shock, so that the velocity entering the compressor is not to exceed 25 meter per second. So at the exit velocity is given 25 meter per second. So it is quite small velocity compared to the incoming velocity. Assuming isentropic flow after the shock. So here you have isentropic flow. So besides the shocks, in other regions it is isentropic. Determine that the area, what area is required, and find the static pressure at the exit PE. So this is the problem. So in supersonic flows, since there is a problem of information propagation from downstream to upstream, this way it will not go. So always problem solving happens in a particular direction, you go from one region to the next. So that is how we go through this. So start in between region 1 and 2, which is bounded by an oblique shock. The angle, semi angle of the wedge is 7 degrees. So corresponding to that there is an oblique shock. Okay, so this is 1.75 Mach number. M1 is 1.75. So we know M1 is equal to 1.75 and theta is 7 degrees and beta is 41.87 degrees. So this is what is known. So from this how do we go through with an oblique shock problem? We have to find the normal component is M1 sin beta. This is 1.168. Okay, so once Mn1 is known, we can find Mn2 by normal shock relations. Substitute the normal Mach number. So it is 0.8627. P2 by P1 is known, if you know this. So it is 1.425 and T2 by T1 is 1.1079. Okay, and M2 is Mn2 by sin beta minus theta. If you do this, you get Mn2 as 1.5. Okay, so P2 by P1, T2 by T1 known. P2 is 71.8 0.25 kilopascal. So 50 kilopascal, which is given over here, is the static pressure. P1 is 50 kilopascal, T1 is 250 Kelvin. So these are static values. So it is 71.25 kilopascal, and T2 is 276.975 Kelvin. So 276.975 Kelvin. From here we can calculate what is density. Density is P2 by R T2, which is 71.25 10 power 3 by 287 multiplied by 276.975, comes out to be 0.8963 kilogram per meter cube. Now we need to find what is mass flow rate. M dot is rho 2 A2 V2. M dot is given. It has to support 10 kilogram per second of air. We need to find the area, that is the area of the intake. This AI is, that is the area that we need to find. So A2, now we know properties in region 2, that is what is entering the intake. So if we know V2 is M2 multiplied by square root of gamma R T2. This is M2 V2 turns out to be 500.4 meter per second. M2 is 1.5 square root of 1.4 287 276.975. So this gives 500.4 meter per second. So A2 is M dot divided by rho 2 V2. You can do this calculation. 10 kilogram per second divided by 0.8963 multiplied by 500. This is 0.0223 meter square. So this is the area. So at this point the Mach number is 1.5. So at this point there is a normal shock. So you have a normal shock here. So this normal shock stands here. So we have to find out the properties across the normal shock in region 3. So M2 is 1.5. So N3 is 0.7. P3 by P2 is 2.4583. Okay, and P03, this is also useful. P03 by P02 is 0.9297. So from here we get P3. P3 is 175.153 kilopascal, and similarly you can get T3 is 365.607 Kelvin. T3 by T2 is 1.32. So you can get P3 by T3 and also A3 by A3 star. You can get this value 1.0943. This is there in isentropic tables, not in normal shock tables. So once all this is known, now we are faced with the point that you need to find out, once the velocity goes to 25 meters per second, what to do. So let's just look at that. Okay, so we will take a look at that point. So 25 meter per second, we are looking at 25 meter per second, it is quite small. Now all through these processes they are all oblique shock waves and isentropic flows. So, they are adiabatic flows, so that means stagnation enthalpy is constant or T naught is constant. This is the guiding principle. So, from here we know what is the velocity at the exit. If we find T naught is for the main flow, we can find T naught by T naught 1. This is for 1.75 flow, it is 1.6125. So, T naught 1 is 403.125 Kelvin, and T e can be found by T 0 minus V square by 2 Cp using the energy equation. This turns out to be 401.88 Kelvin. This is V is at the exit 25 meters per second. So, T e is known. Okay. So, what is the Mach number? M e is V e by A e, which is 25 divided by square root of 1.4, 287 and 401.88, which is 0.0622. So, it is quite small. At such small Mach numbers, you can also assume that T naught and P naught is approximately equal to P and T. It is not a bad assumption, because you see the difference between them is hardly 2 Kelvin. So, that assumption can also be made, or you can continue to pursue with actual numbers. So, if M e is known, then A e can be found out. A e by A e star can be found, it is 9.3255. Now, we need A e by A I, that is what is the area ratio A e by A I. So, this is A e by A e star multiplied by A e star by A I. Now, for A e by A e star, the value is known, 9.3255. Now, after the shock, the flow is isentropic. So, if we take the Mach number after normal shock, so for that the A star, A2 star, A3 star will be equal to A e star. Okay, so, this will be equal. So, we can write this as A3 star by A I, that is A3, the same as A3, and this we had found, it is 1.0943. So, 9.3255 divided by 1.0943 is 8.522. So, you can get the exit area as 0.19 meter square. Okay. So, what is P exit? This is what is needed. For this we can use pressure ratios and calculate it, but now that we have calculated mass flow rates, static temperatures and velocity is 25 meter per second, we can go ahead and convert this rho V A, rho E V E A E to P E by R T E multiplied by V E multiplied by A E. Okay, so, A E is known, V E is known, P E is not known, T E is known, R is known, equal to m dot. This is 10 kilogram per second, it is known. From here you can get what is P E, it is 42.82 kilopascal. Okay, so, you see, so this particular concept had a diffuser problem, but the diffuser also had oblique shocks ahead of it and a normal shock at the diffuser. So, entry of the diffuser. So, you see this has multiple concepts. So, From here on you see that problems involving all these applications, nozzles, diffusers, they will not be having only one concept, they will involve multiple concepts. So you have to take care of that. So now let us go to the next problem. If we wish to design a supersonic wind tunnel which produces Mach 2.8 flow at standard sea level conditions, that means at the test section it is standard sea level conditions and Mach number is 2.8 and mass flow is given, m dot is 14.6 kilogram per second. Calculate the necessary reservoir pressure and temperature, nozzle throat and exit areas and diffuser throat area. So basically it is a you have this picture schematic should come there. So what is nozzle throat, is this nozzle exit area, and given that this is m equal to 2.8 and P is equal to P test section. So P1 is standard sea level 101.325 kilopascal and T1 is taken as 288 Kelvin. Okay. So these are the conditions, and what should be the diffuser area. So area of the diffuser throat. So what are these, what is required? So we know the wind tunnel Mach number 2.8. What should be reservoir pressure? We know pressure is 101.325. In ideal operating conditions Mach number is 2.8. So the pressure that should be given there at P naught is going to be corresponding to 2.8. So P naught E by PE is 27.14 and that implies P naught is 2749.96 kilopascal. That is in bars it will be 27.5 bars. It is quite high pressure you have to give, 27.5 bars. Okay. And what about T naught E? If you have to achieve 288 Kelvin at the test section, then as flow expands through the nozzle temperature will reduce. So that means much higher temperatures has to be given, and that is, this ratio is 2.568, implying T naught E is 739.584 Kelvin. So much higher temperatures need to be provided. So what is the area of the wind tunnel test section? That is the exit area of the nozzle. We know mass flow rate, m dot is 14.6 kilogram per second, and pressure and temperature are known. So from this you can calculate density P by RT. Velocity should be found. So velocity is Mach number 2.8 multiplied by square root of gamma RT, gamma 287 multiplied by 288. So this is velocity, it turns out to be 952.48, gamma is 1.4. So area is m dot by rho v, rho ve, this is 0.0125 meter per meter square. Okay. Now for this Mach number we know AE by A star, AE by A star which is 3.5. So during correct operation the throat will work at Mach number 1, so that is equal to A star. So throat area is, A throat is 0.0125 divided by 3.5, this is 0.00357 meter square. So, we know the throat area also. Now, the next point here is we have to find what is the minimum area at the diffuser. So, this should be such a way that the wind tunnel will start, it cannot be the same as the nozzle throat area. So, that is the highlight here. So, Mach number is 2.8, m is equal to 2.8. So, the way it is designed is there is a normal shock standing at the test section. So, for Mach number equal to 2.8, if there is a normal shock, P naught 2 by P naught 1 across the normal shock is 0.3895, and we use the fact that P naught 1 a nozzle throat is P naught 2 multiplied by diffuser throat. So, diffuser throat is nozzle throat multiplied by or divided by P naught 2 by P naught 1. So, this is known. So, diffuser throat is 0.00955 meter square. So, diffuser throat is larger than the nozzle throat. So, the aspects of wind tunnel starting is considered here in order to look at the nozzle and the diffuser throat areas. So, with this the aspect related to starting of diffusers should be covered, and now we look at several problems related to different concepts in varying area ducts. So, we will go through a few simple problems and two problems that involve multiple concepts. So, that would be done in the coming classes. Thank you.